Yeah, okay, welcome back, everyone. Today it's my pleasure to welcome Daniel Lengyel, who will be talking about gradient estimation. Yeah, thank you, Daniel.
Okay. Hi, everyone. Yeah, today I want to talk about the work I've done primarily during my PhD, which is on gradient estimation methods. And even though gradient estimation methods seem like they have been quite well explored, especially past finite difference methods, I kind of want to take another perspective and show that there's quite a bit more to do, and that there are quite a few interesting connections to some modern methods, some derivative-free methods, and that it pops up in like surprising ways. So yeah, I want to talk about that for a bit today. Okay, so the rough outline will be, okay, why do we want to study this problem, or really what drives me to study sample set selection for gradient methods? I'll briefly talk about what that is here. Then I'll talk about the definition of gradient estimation and the method that we'll be using to do so. Then we talk about objective functions, how to assess optimality for the elements that you want to find. Then we talk about the results that we have found for the two different instances of the simplex gradient. And then we look at the actual applications and where this is actually going to be useful. And the areas really that motivated me to go into this topic, because we were, for example, looking at interacting particle methods or derivative-free optimization methods, maybe your inverse Kalman filters or your iterated filtering methods. And it turns out that implicitly a lot of the updates are done via gradient estimation method. You wouldn't see it normally, but if you look closely, that's actually where it is. And I think there's some recent research actually showing also this connection more explicitly. And then I'm going to talk about piecewise linear functions, which are our favorite neural networks, and how there's also a link to that that could be explored. Okay, so what's the motivation for looking for these optimal sample points? And I guess kind of a rough overview of what the mantra is with this work is, generally we're given some data and you want to find what the best model is, right? You're giving financial data or maybe weather data, and you're saying, okay, what kind of model do you want to fit? But sometimes you also want to understand the data better, and it's hard to really do so. So you might go the other way, say, okay, I have some kind of model that I think is appropriate for my system, and then what kind of data would be good? This might help you actually select data from the data set, know what's corrupted, what are the outliers. It might also inform where to select your next data points. And this is kind of the approach that we want to take here, like take this reverse mode, say, okay, let's say we have some given model, we think it's actually a pretty good approximation of what we actually want to estimate. Then what is good data for that? Like, what kind of data should I provide that's good? And obviously some classic methods would be maybe some kind of Bayesian methods, but here we want to focus a bit more on on some deterministic methods for one reason or another, as we'll discuss later. So what exactly is this gradient estimation problem, and what is the simplex gradient? I want to give first a motivating example of what kind of problems we face when we select data points for the gradient estimation problem. First, let's consider this quadratic. We have the quadratic obviously in the solid line, and then the dashed line represents its derivative at the point -1. And now let's say we only have noisy instances of this quadratic. So we have the green and red line. Hopefully that's visible to everyone. And these are noisy observations really of our system. So we can think it's one time point we have observed the system to be that, and another time point we have observed the system to be given by the other line. Now, your task is to say, okay, I don't have the analytic form of the true function, but I want to select points and then just interpolate linearly between my estimation point -1 and the point you selected. And now how does this noise influence you? Well, if you're far enough apart, if you select something at 0.5, if you say, okay, I think 0.5 is a good point to select, and then you draw the line between the value that you observe and the estimation value, -1, you get something that's fairly robust, as in like the variance is maybe not as large, but you're quite biased. You have quite a large approximation error because you're not really approximating the function locally well enough. But if you do the reverse and you go a bit closer, you're actually faced with the opposite. Your approximation error is somewhat low, but now your noise error dominates and yields quite a bit of variance. So you still get a large mean squared error. The question then becomes, okay, how do you balance these two things? And how to optimize for that. And this is quite a nice problem, right? I mean, in machine learning applications, we have our bias variance trade-off. And in some ways, this is like one of the most fundamental ways it can pop up, right? If we want to approximate a function locally and we have a bunch of data points, if they're too close together, we might get instability because even small variations due to noise can lead to very poor fits. So here, we want to look at it from this gradient estimation perspective. Just to formalize what we're actually looking at, we're looking at a system that's corrupted by some noise. We assume mean zero, errors are added with bounded variance. We also assume constant variance, mostly because we are working in local domains and we hope that the variance will be constant, but there's some open work to make this more general. And we also assume that function evaluations are expensive, so you can't just evaluate the function a million times and average out the noise. Otherwise, it would be easy. So you kind of want to have a balance between the number of function evaluations and how good they are and like the accuracy you want to achieve. Okay, so what kind of methods are available for this? The classic methods are finite differences, then you have your SPAL methods, design of experiment schemes, and the simplex gradient. Finite differences, I think the most common one, it's really just take some kind of grid and you take your differences, you divide by the difference in the x values and you get some kind of local estimate of your gradients. However, they are not very robust or, well, they're not very flexible because you're given some kind of layout. Instead, it can actually be generalized by the simplex gradient. The simplex gradient also generalizes the others in some sense. Don't have to go into it, but the simplex gradient is actually defined as the gradient of the linear least squares approximation of the function fx on some set. And the set of points at which we evaluate the function is commonly called the sample set. So now we can make the things we've been talking about a bit more precise. The simplex gradient is very nice because it's flexible, as it allows us to choose any kind of sample set. As you can see here in this plot, we have chosen these scatter points as places where to evaluate the function. And now you just fit a linear function to those set of points. You take a linear function because you think the gradient, locally the function is linear. So you think a linear function approximates as well. It's fairly robust. And this is really the most general form you can put it in. The only flexibility you have is a priori choosing the sample set. In this case, in this picture, we don't have any noise. So again, putting the points close together would give you the more optimal gradient. But as you can see here, if they're far apart, you actually get an approximation error again, which is an issue. So we're now tasked, and maybe this makes it even more clear why we're studying the gradient estimation problem, is really we're asking what kind of points are the best for a linear approximation of a function locally, which we found to be quite a nice motivation to pursue this study. So now what's the sample set we were talking about and what kind of structures can it have? Because in the end, that is really what we're trying to optimize for. So the general simplex gradient sample set is given in figure A. So we have x0, which is the location of the gradient estimate. Then we have these xi's, which are the other sample points, and the si's are difference vectors. They are the difference between your xi and x0, and they point in the direction which they go. And then now we can actually look at the structures of different types of sample sets of the simplex gradient. One is the fully determined method, where you have in a two-dimensional plane, you have 3 points because that fully determines actually your affine plane that you fit for the gradient. You need at least 3 points, and in higher dimensions, you need d plus 1 points. So it grows linearly. Well, they both grow linearly, but it grows as d, essentially. And has certain approximation properties. Then you have the centered version, which reflects each point. So you get 2 d points. So you have to use twice as many points as for the fully determined. The centered will not be fully determined anymore. So you won't be able to just fit a full plane into it. But it has some other nice properties as it gains you gain an error order term. So you actually improve accuracy, but at the trade-off of the number of sample points you need. So the fully determined is actually an approximation or a generalization rather of forward finite differences. And then the centered simplex gradient naturally would be the generalization of the centered finite difference method. And now the question will be, what would be this optimal sample set to choose for each of these methods? And how would they look like? What geometric properties do they have? And this should tell us something about the function locally, like how it behaves, what it means to actually fit a linear function locally. So actually learning the structure gives us quite a bit of insight about the local function structure and how linear functions behave. And to make the notation more clear, we say the sample set is given by this mathcal x. X0 is again the point at which we estimate the gradient. Then we have the difference matrix S given by the concatenation of all of our difference vectors. And then we call the function difference vectors f, x, I. There should be a delta. So this takes in the difference between the sample point function evaluation and the evaluation at x0. And now we can succinctly write the simplex gradient, which is really just the gradient of your best linear approximator, and it's given by S transpose S inverse S transpose delta F, the common linear regression form. Right. Again, very nice. We're just now asking what's the optimal data for like maybe linear regression, right? How would we most accurately approximate a function locally? If that's the interpretation you want to go with, instead of just saying we want to do gradient estimation. All right, what we need for this is some way to assess how good a sample set is. And what you can do is you can look at your mean squared error and you can start decomposing it. So you get one part the approximation error and the other part the noise error that we were talking about earlier. The approximation error, as you can see, we got rid of the tilde. So that means that this is really on the true function. So how well would the simplex gradient behave on the true function? That is the approximation error. And then the noise error actually doesn't depend on the function at all. It's really just a property of the noise that we added. But still, it's a property of the sample set. So we still need to make sure that the sample set is well conditioned. So since f can be arbitrary, it is actually pretty difficult to minimize for the sample set here. You would have some kind of quadratic, some optimization problem that's quadratic in the dimension, and you would have some generic f, which might be difficult to work with. Instead, we want to maybe approximate the function locally and better understand how it behaves, right? So we would want to go for some kind of Taylor expansion. This is quite nice because polynomials are very well representative of a function locally, and they tell us quite a bit about its structure. So then the question will be how, what is the sample set for maybe a quadratic or third order polynomial, and how would the sample set for those functions look like? And they should be good proxies for the actual true function I'd be looking at. To make this more precise, first some notation. So alpha is a multi-index, then rewrite alpha, this is the order of alpha, the degree. And then x alpha gives you kind of this product exponentiated. Then you get this factorial notation, which is the product of factorials. Then when we take a partial with respect to alpha, we get partial alpha 1, partial alpha 2, and so forth. And now this is the guy that we care about. So when you have a higher order derivative in a multivariate case, you actually get an induced K form via this derivative. And it's also a homogeneous polynomial. So rather just think of it as a polynomial. Homogeneous because every term in the sum of the polynomial has the same order, which is quite important for some of the proofs, but we won't get into it. And then you can write this form as the sum over all alpha such that they have order k with the gradient with respect to alpha, or the partial derivative with respect to alpha, k factorial over alpha factorial. This is necessary for the Taylor. Well, no, it's just how it's given by the k form. And you differentiate f of x and s alpha. This should be flipped. And then we write this in vectorized notation. So if we have some set of difference vectors, we would write it as a column vector. So if we plug in mathcal s into here, it's just a column vector of polynomials. So it's quite nice, right? So now we can use this expression via the Taylor's theorem to approximate this approximation error. what we can then do is we substitute. So here we get the second order derivative when we use the fully determined sample set. And when we use the centered sample set, we get third order derivatives. Here, we see that the order of our error is cubic in the first term and to the 6th in the second term. And this means that when you're close locally, the error in your approximation via the second or third order derivative vanishes pretty quickly. Again, quite a nice property telling us that polynomials approximate this function pretty well. Obviously, an important question is, if we assume that we can approximate this function with a polynomial, then how can we actually work with gradients, or how can we hope to actually use this to get a better gradient? And we'll talk about this in a bit more detail later, but I think the general idea is that sometimes you have some sort of idea of the function, how it looks like globally. Imagine you have some kind of past function evaluations of your function. Then you could use a data-driven method to fit a global model to those points. And sometimes that global model can then actually be used as a gradient estimator. You just differentiate it analytically. However, it sometimes is the case that just the gradients aren't as accurate as you want them to be. So the global model might be fine, but it's rather coarse. So it doesn't give you a good gradient estimate, but it might give you a good enough Hessian or third order estimate to inform where to sample your points to get a better gradient estimate locally, right? So we really use some sort of global information to just slightly better inform how to sample or how to construct a sample set. That's one reason. And the other reason for going forward with this is actually just understanding what the sample set looks like theoretically. All right. Let's see. Next slide. So now we can actually consider the objective function for each case, for the fully determined and for the centered case. For the fully determined and the centered, what we do is we just take the first term of the approximation error from earlier, plug it in, and we replace the higher order errors via this constraint. We say that h upper bounds here the L2 norm of S, and here it upper bounds the radius. The choice for the bound is a bit technical. You could use the radius for both, or you could use something else for both. For this guy, it happens that one of the main results can be found analytically, as we'll see in a second, via this constraint. For the other one, it seems the radius is good. In practice, it doesn't make too much of a difference, but in the papers, we have also generalized this quite a bit. For this case, we just go with these two. Okay. So now we get to the first exciting point, I think, about what do these optimal sample sets even look like. We have talked about what's a simplex gradient. It's the best linear approximator of your function locally. And it requires a sample set to be given. It requires you to tell it, where should I evaluate the function, such that I can use that information to now construct this best linear approximation. And now we want to learn, what does this structure actually look like? What kind of sample set structure do we get that's optimal for both the centered and for the fully determined case? And what can that actually tell us maybe about the function locally, or what kind of insights can we gain? We will start with the centered case, just because I feel like it's a bit more intuitive, or it's more easy to see what the proof could look like. So we'll start with the centered simplex gradient. And if we look at this objective function carefully, and we look at this first term first, this is a vectorized version of the homogeneous polynomial, and it's from S1 up to S2D. And because actually we have symmetric properties, the last D elements are the same as the first D elements. And we see that this is minimized if we can make this 0, then this is as small as we can get. And to make it 0, what we need to find are SI roots. So we need to find these SIs, the roots of this polynomial. So really, it's now just, I have a polynomial of third degree that's homogeneous, and I want to find D roots of that. And D roots suffice. because if you flip them, if you invert the sign, you still get a root just by properties of these polynomials. We don't have to worry about that. So we just need to find the roots, and we can minimize this. Okay, now the second term is still here. So the noise error is here, and it turns out that that's minimized when the sample set is orthogonal, which is already the case for the centered finite difference method. But maybe the alignment of the difference vectors doesn't actually allow for the roots, or it doesn't give you roots. So maybe it's just not right aligned. So we'd have to find the right alignment. So then the question becomes, to minimize this, if we can, well, rather, if we can find the orthogonal roots of the polynomial, of this third-degree polynomial, then we know that we have found the global minimum. So that should be maybe the first goal to go with. Let's find these d orthogonal roots, and then we should hope for quite a bit of an improvement. And let's see what this actually might look like. What are we actually looking at here? So in this first picture, we're looking at a visualization of the roots for a 2D polynomial, and the points are essentially the roots. So you can think of it like maybe a contour map, and actually would have to think of, because these are homogeneous along the whole line, you get roots. But let's look at all the unit roots. So all the roots that are a unit distance away from 0. And we see these dots. And again, we can find actually some orthogonal roots along the coordinate axes. The same in the 3D space. We again plot the unit roots. So all roots that are unit distance away from 0 for this polynomial. So here the input space for the polynomial is 3-dimensional. And we just want to, in this domain, we want to find all the unit roots. And again, along the coordinate axes, we can find the orthogonal roots, or at least it looks like it, right? Like, I mean, we'd have to confirm, but it looks like it. But there are also, you can easily construct, well, not somewhat easily construct cases where you cannot find the orthogonal roots. Again, here in this 2D case or in this 3D case, you cannot find these the orthogonal roots. So what gives? As we've said, this problem simplifies to finding the orthogonal roots. Since we want real roots, and maybe some people are familiar with this, the whole algebraic geometry stuff, or just if you work over algebraically closed fields, you would find these roots if you made the right assumptions, because you have, let's say, over complex numbers you could. But since we have real roots, this is not guaranteed. We cannot guarantee that we can find the orthogonal roots. Doesn't mean that they don't exist yet, but we can't guarantee them. There are methods from real algebraic geometry that allow you to find existence and actually find them. And they're based on like Tarski-Seidenberg, but they have doubly exponential runtimes, and I could never get them to work for even like very, very low, like 2-dimensional problems or 3-dimensional problems. And the first negative result is that we actually have a proof that shows that they do not exist. There exist polynomials. There always exist polynomials for each dimension that do not have the orthogonal roots. So that's the first negative result. Or maybe the only one, because the next one actually tells us that the next base case actually holds. It holds that we can always find d-1 orthogonal roots. And that's quite exciting, right? Somehow it holds that we prove actually this more strong statement that for all odd degree homogeneous polynomials with more than one variable, there exists d-1 orthogonal roots. So this is quite a nice insight, just like from a polynomial perspective, like somehow for these special types of, well, not that special. I mean, it's just the polynomial induced by a third derivative. For those, you can always find d-1 orthogonal roots. And remember, to find the minimum for the sample set, or to find the minimizer, we need the orthogonal roots. So there are multiple ways you can actually handle this in practice, and some things we propose to actually work with this insight. So one you can do is, first, what you want to do is you want to find d-1 orthogonal roots, and set the step size to h, this constraint that we had earlier on the radius of the sample set to make sure that we don't have higher order errors. And then the final vector, we can either just choose the next orthogonal vector, extend the set of vectors by 1 and make that one be orthogonal to all the other ones, and just scale the size of that appropriately to, again, have this noise approximation error trade-off that we talked about before. The other is you can maybe even use a numerical solver. So let's say you can think of this method that we have proposed here actually as a dimensionality reduction method. I can find d-4 orthogonal roots, so d-3, d-2, and so forth, and leave the remaining space free. And then I can say, okay, a numerical solver can come along and solve the remaining dimensions and find the optimal solution there. So even for the last one, it could just like try a bunch of different directions and see which one gives you the lowest objective function in total. Now, the immediate argument is, okay, why didn't you just do that in the first place? And well, it turns out that actually runtime-wise, it just isn't feasible in higher dimensions. You really do need this dimensionality reduction property. As you see here, we have BFGS as the numerical solver we use here. If we use central difference is very fast because it does everything in linear time. And central difference is basically this exact what we had done, but just a fixed orthogonal set, which is coordinate aligned. It's very fast to find the optimal set here. Orcas grows reasonably fast, or slowly, I don't know. And then the combined method, Orcas BFGS, is obviously slower than Orcas by itself, but as BFGS goes into higher dimensions, we get actually significantly worse runtimes. So it's quite nice. So actually, just in high dimensions, I can't even get it to work at some point anymore. It explodes very quickly. So this dimensionality reduction method really helps us a lot. And for performance, we actually see that the black line is the lower bound. This is the best case performance that we could hope for over some randomized polynomials. We actually find that for well-conditioned problems, we hit that lower bound for all of our methods, and central difference is like a couple times worse. And this is, since I constructed this example, I could make this gap wider or larger depending on what kind of problems you want to solve. So this gap can be, yeah, we have some analytic results that say that depending on some function properties, this gap can be very large. And on the other side, when you have a ill-conditioned polynomial, or let's say one direction is like very, very large while the other ones are rather small in scale, then you get different behaviors where actually Orcas doesn't behave that well anymore. But again, the Orcas with numerical methods or the numerical solver themselves actually, again, is close to the lower bound and an order of magnitude better than the other methods. Intuitively, this happens because imagine your space where you find your difference vectors. Sort of the last difference vector that stays free will be pointing in the direction of the largest increase, or the ill-conditioned direction. So you actually get quite a bit of an error in that direction. So you need to avoid that, and you need to sacrifice orthogonality, which is why the numerical solver helps there. We have more results in the paper, but that intuition is, I think, enough for this. And this is why the numerical solver is nice. You could also find some other heuristics or find some maybe closed form solutions, but the numerical solver works so quick in like 2 or 3 dimensions that this seemed always appropriate. Okay, any questions? I then want to go into the second sample set that we considered. Okay. Yeah, also anytime during the talk, any questions are welcome. I know maybe this is not super super well known, this field, so I'm happy to talk about anything. Okay, now we're going to look at the fully determined simplex gradient. This is really your linear interpolator. So here you have a sample set that has d+1 sample points, and you're going to find linear interpolation. And you want to find the sample set that does that the best. Here's the theorem that we have for this, and this is going to be the most math I'm going to throw in here, because it's quite unwieldy. But actually, it turns out to be a very nice interpretation for what's happening. In the previous case, we were just saying, look, actually an orthogonal set is pretty nice. Let's rotate it just in a way that we can find roots of the polynomial. We don't have to do much many crazy things. We just rotate the sample set in a way, maybe even keep it orthogonal, such that we find roots. And this is the benefit over central differences in that case. Central differences are already orthogonal, but just not rotated well enough. For this finite for this fully determined simplex gradient, for the generalization of the forward finite difference methods, this doesn't hold anymore. You actually change the structure of the sample set quite a bit. And there are some geometric insights here that are just interesting and nice. And they kind of behave the way you would intuitively hope for. So what are the results, the theoretical results that we have? Well, first of all, we can write our optimal sample set as this matrix. If we have our Hessian, the second derivative of our function, given by in diagonal form, then we just need to rotate the right-hand side of this expression, which is a singular value decomposition. So this guy just rotates your sample set that you find in the diagonal space to be in the real space. So then you have U star, lambda star, and V star. Lambda star is given by this optimization problem. U star is surprisingly just the identity. And V star is the Hadamard matrix, which the Hadamard matrix actually gives you many nice properties, it turns out, on like how it distributes the sample points geometrically. And this lambda star problem is really, even though it looks a bit not so nice, it's really a simplified form of the previous objective function. And instead of deep squared variables, you only have d variables. And because we used the L2 norm to bound our sample set, we actually have an analytic solution for this problem. I'm not going to write it out, it's pretty ugly, but you do have an analytic solution for this form. So you get around any kind of numerical solutions. But this objective function by itself already displays many nice properties. And I want to highlight kind of what the structure of the sample set inherits from this. And I think as a first precursor, I want you guys to look here. This is a sum inside of the square, and the di's could be positive or negative. So maybe you can get even rid of these by making them 0, which is sort of similar to finding the roots from earlier. So you get rid of this approximation error by finding lambda i's such that this guy becomes 0. And this is exactly what we find in the case of indefinite Hessian. Here, just a quick note on what the geometric properties look like. So for now, we'll assume that the Hessian is actually in the diagonal space. So the Hessian is just diagonal. This is without any loss of generality. And the norm is just given by the sum of the root mean square of the singular values of your sample set. And then actually we want to look at the angles that each of the sample set points or the difference vectors make with the coordinate axes, which are always also the curvature directions associated with the eigenvalues of your Hessian. So the first coordinate direction would be, for example, the direction of lowest increase, just by convention here. And then the last coordinate direction would be where your function increases the most, according to its second derivative. And we can see that this is given proportional to how much weight each singular value has, according to all of the singular values. So the larger one of the singular values is of the sample set, the more it's going to be aligned with that curvature direction too. We'll see in a second why that's interesting. First, the indefinite quadratic. And here, let's look at the first figure A. And as you have already said, what we would want to have is exploit the fact that there are positive and negative eigenvalues of your Hessian and find roots of your polynomial, just as we have done before. And this is exactly what we want to do here. We want to align our sample set points along 0 sets of the quadratic, of this quadratic given here, this S1H S1. All right. And the closer we can align them with those 0 sets, the lower we make the approximation error. Obviously, when you have more ill-conditioned Hessians, the 0 set lines will change a bit. So you will have to maybe sacrifice some of the orthogonality. But if you have a well-conditioned indefinite problem, you can fully remove the approximation error while staying orthogonal, just as we have done in the previous problem. And this is also what we see in the mean squared error case. Depending on the condition number, we improve. Well, we're always better than just 4 differences, but we also see quite an improvement on low condition numbers. And the intuition also holds up that in C, we see that this is because we were able to increase the sample set size, or radius rather, without sacrificing any approximation error, right? Because the approximation error is good because along those 0 set lines, we're doing nicely. Now let's look at, okay, now we have our theoretical results that actually also justify this. They say that our sample set is going to scale with h, which is the bound that we gave it. So the larger h is the larger the sample set is going to become, which means that the smaller the radius is going to become, and also obviously the approximation error is going to go down. or will be adjusted according to it. And then the difference vectors balance between orthogonality and being aligned with the zero set lines. So we can prove this also analytically, that this is actually the behavior that you will see. Now, I think the final insight that I want to talk about maybe ties up these things nicely, and maybe also gives another perspective on why we wanted to use the zero set lines, what they actually mean in practice and why they're useful. So recall the approximation error is this guy, and then the noise error is this guy. So you have this trade-off: the lower you make approximation error, the larger you make noise error, etc. So what we were doing earlier is we were trying to find directions in which the gradient doesn't change too quickly. By definition, along a zero set line of, let's say, your Hessian or your third order polynomial, the gradient will not change at all. So you can go in that direction indefinitely, and the gradient will stay constant. Whatever the gradient was at your point, it will stay constant along that line, which is why we were choosing those. Just intuitively, we just wanted to find directions where the gradient changes the least, so that we can make our sample set longer along those points. Because then we can mitigate the noise error that we have, this overfitting locally. So the more we can really change the structure of the problem and see, okay, where do we not incur as much loss? We want to go along that line and kind of increase our distance there to mitigate any effect that noise might have. Now, when you have a definite quadratic, you don't have any zero set lines anymore because you have positive eigenvalues for your Hessian. But you still have low curvature directions. There might still be a direction where the curvature is lower than in all the other directions. So you might think, I want to exploit that and use that insight and align my sample set points along that curvature direction, where again, the gradient changes the least, and I can increase the sample points or the length of the difference vectors to mitigate the noise error while not incurring more approximation error cost. And while this is intuitive, it's also confirmed both empirically and, again, theoretically, we can show this to be the case. Here we see in the first figure that exactly these two difference vectors are aligned with the lowest curvature direction, where the gradient changes the least. And the set 4 difference cannot, again, adjust to these points, cannot adjust to this kind of curvature inside. It just like is stuck to its structure. And here we can see that the more ill-conditioned the problem is in this case, because we can exploit the low curvature more, the better we do. Again, magnitude's better. And in the last figure we see, again, this is because we are able to increase the sample set radius more. So we're able to decrease the noise error while not really incurring more approximation error costs, but exploiting these low curvature directions. So here we have this in theoretical form. Not a lot of stuff to worry. Here, just see that lambda 1 over d is how the norm of S1 of all the difference vectors scales. And L1 is associated with the smallest curvature direction. It will be the largest. Here we can see that the smaller D1 is, the larger this difference vector is going to be. And here we can also show the bound on the angle to the low curvature directions. The lower D1 is, and the larger all the other elements are, again, the more ill-conditioned the problem is, the smaller this is going to be, and the tighter the bound. Okay. So before we go on, I want to talk about what we actually saw here. We were seeing these sample set points, or where to evaluate our function, and looked at the kind of structure that they would exhibit to provide optimal gradient estimates, optimal mean squared errors. We kind of want to use this insight of like, maybe we have some local insights about the geometry and know that in this direction, the gradient changes less, or in this direction, the gradient changes the most, and we want to avoid that region. And now we have a theoretical insight into how actually these things would have to change. The common wisdom up till now was to actually just keep everything orthogonal, precisely because the noise error is orthogonal in an absence of any kind of information. We shouldn't change anything. Even though a lot of methods do use some insight about the local curvature to adjust the difference vectors, but they did not use the insight of maybe the relative importance of one direction to another. And just the insight was that we needed to keep these difference vectors orthogonal to each other for no big reason. And it's also not a priori obvious that this would be the bad thing or isn't optimal. mostly because we could think of an ish setting where just changing the approximation just doesn't pay off to like get rid of the noise here. Maybe it just is the case where yeah, but it turns out that it's not the case. That actually pays off to change the structure of your sample set, to maybe adjust quite a bit to whatever local information you have, and sample your function according to this. Now some applications and where we can actually see this and actually see maybe some performance of how this behaves. The first thing you want to look at is sensitivity analysis, which is really the most fundamental assessment of this method, because we just look at the gradient. How good is the gradient compared to the true gradient? Of course, you can have other different sensitivity analysis metrics, but let's just say I want to find the most optimal gradient because I want to know how the function changes locally for some kind of sensitivity in chemical processes or other kind of environments. And for this, we developed this global model framework, to which I already hinted before, where we sort of say, look, in a lot of environments, you already have a history of function evaluations. Even maybe in some derivative-free environments, we already did some kind of evaluations of your system. So these might give you a coarse model. They will never be good enough. Not never, but mostly they won't be good enough to give you an accurate gradient estimate. But they might be accurate enough to give you a good enough Hessian estimate or third order estimate, just to tell you in which directions are more important. And obviously there's more refinement that could be done, right? We could kind of see, given the error of the global model, how should we adapt our previous theoretical assumptions, right? Because early we assumed a perfect Hessian. And maybe we can incorporate this noise in the global model into our system. Maybe we're kind of overfitting by using this kind of theoretical optimum just fully on the on the information given here. But it seemed like actually we did get quite a bit of a performance boost, just naively using the two together. We sampled some points, we fit a data-driven model to it. In this case, we used the cubic spline radial basis, and then we took the second or third derivative of that function and used that to inform our gradient estimate. And to make comparisons fair, we also obviously include the gradient estimate given by the global model. So if we just use the global model, what kind of gradient estimate would we get? Here's the first case, which was the first case, the centered simplex gradient. And we see that the solid lines are without the global model, just as a baseline, just to see how good could we get. And then the dashed lines are using this global model. And if you look at the first figure, we see that the solid lines give you, again, an improvement of
Okay.
Okay. And we can see that, again, we have an order of magnitude improvement. And if we use the global models, we also perform better than central differences, both optimal central differences, where we give it full information because we can actually adopt things according to the information given, and with the global model information, which is quite nice. So we actually get quite a bit of improvement. We see that they're quite similar, even though that here there's a bit of a gap in performance between the orcas and the orcas with the numerical solvers, as we discussed earlier. But we think this kind of disappears because, again, because we give it a noisy estimate of the third derivative, it doesn't perform as well. And here in the second plot, we see actually that the global model performs worse. Towards the end, it starts approaching the performance of central differences, but we see that already here, the performance around 1000 or 800 bottoms out for these other methods. And as we go in higher dimensions, obviously it's like a 4-dimensional problem. To be honest, you can't really hope to go very high dimension. I mean, depends on what kind of assumptions you make about your problem. But in high dimensional problems, you just don't have enough data for the global model to work that well anymore, because you need to approximate the local structures sufficiently well, and you just kind of lose any kind of approximation power there, especially for using third order derivatives, which is just more to ask for. Here, the exercise was really to show that theoretically what happens, and also to show that it could be empirically viable or in practice, but you'd have to maybe work a bit more on understanding how to combine the two and see see what kind of noise in your third order estimates, how they influence your actual gradient estimator. Now for the curvature line simplex gradient, which is the second approach where we actually use Hessian information. We ran it on a self-growth ODE, so simulating cancer growth. And here we have two figures, one looking at comparisons using our method using the true Hessian and one with the RBF Hessian. And let's look at the first figure first, just as the baseline. So what we do here is we take the ratio of the other method. So let's say the forward difference method with our method, and we take the log of that. And this is telling us that if, for example, we have a 2 here, it says we're 4 times better on average on 100 samples of this function. And for this guy, we're like 2 to the 5 times better, right? So we get exponentially better for these other methods. And yeah, we do this on like a couple hundred data points of this function. So we sample the ODE at a couple hundred data points. We evaluate the gradient there and see how well we perform, which is why you get these box plots. And again, we see that in the best case scenario, we actually do better than central differences, which happens just because of data specific properties for this specific cell growth ODE. And then if we use the global model, the RBF Hessian, we see that we're slightly worse than the central difference approach, but we're still 4 or 5 times better, 6 times better than forward differences, even using the exact Hessian. This is important. Even forward finite differences using the exact Hessian, all the information you can give it, all these other methods, basically. This is really the state of the art that other people have been using. We can still do quite a bit better by using this extra information gained from the global model. And again, we see that we just outperform the global model still. So the global model doesn't give us good enough gradient estimates, but it gives us good enough Hessian estimates to inform our sample set selection just slightly better, to actually provide us with more accurate gradient estimates. Okay. And now a bit of a look forward, or what else one can do, and sort of seeing where the motivation of all this came from, and maybe provide some more excitement for this kind of gradient estimation, why these sample sets are interesting. And I think we really started with looking at interacting particle methods and optimization methods and evolving particles over time. This was our idea. We wanted to like see how do we update particles perfectly to maybe represent some kind of distribution, or maybe, you know, to be able to sample from a distribution, to maybe track some kind of properties of the function. And I kept finding this kind of simplex gradient structure in it. And we kept working on it, and we were kind of confused. Okay, if we're doing this kind of heuristic update, but we have no idea of how these sample sets actually evolve over time, or what an optimal sample set is for the structure, then we're kind of just doing it by intuition. And it would be quite nice to get some stronger insight into what an actual good particle cloud would look like if we really use a gradient estimator implicitly to update our particles. Then we should know what a good implicit gradient estimator looks like. And it also makes sense that these methods will use implicit gradient estimators because we're optimizing for something. And to update to the next step, you need some kind of idea of how to increase or decrease your values. So it also makes sense that we would find these gradient estimators. I just quickly want to mention 2 specific areas where you can find it. So one is in iterated filtering. Here you use some kind of recursive sequence to maximize your likelihood function for partially observed Markov processes. And here, the solution of the filtering problem is this guy, which by Stein's lemma actually gives you the smooth gradient. And there has been work on showing that actually a smooth gradient, or a Monte Carlo estimate of the smooth gradient, is actually worse than just a deterministic simplex gradient, because because of variance reduction properties. You don't have the variance in actually sampling from this distribution, which seemed kind of counterintuitive at first, because we thought we would get better properties, because Monte Carlo estimate of some integral kind of doesn't depend on the dimension as much. And here it's already, you can see the resemblance of the simplex gradient here as well. If you discretize this, this could be the sample covariance, which is exactly our S transpose S inverse. And this is our S transpose delta F. The delta F is disappeared here because we assume a symmetric distribution. So here already, this, even though we didn't think of it that way, if you actually look at this likelihood maximization problem in iterated filtering, the form looks very complicated and very difficult to parse. But then it turns out the simplex gradient is right in there. It just uses the particles that you evolve over time to estimate the update step. A similar case in this Kalman inverse. So this is something that Andrew Stewart, I think, has been working on quite a bit. They do Kalman inversion, and some other people have found statistical linearization in it, which is something we've also found at the same time for these methods, that somehow they just do kind of implicit simplex gradients. And they coined it statistical linearization, but it really is just a simplex gradient, because it's just, again, your sample covariance S transpose S multiplied by your covariance of input and output, which you can again interpret as this S transpose delta F tilde. So again, you're just, the particles that you're updating according to the simplex gradient. You just find the best linear interpolation of your points, and then you take the gradient of that and go in that direction. So this was kind of the insight into the interacting particles and optimization literature. And I think the last thing I want to mention is the piecewise linear functions. This is something I hinted on in the beginning as well. And this kind of makes sense if we look at the gradient estimator again as a best linear approximation locally. You can then think of your piecewise linear function you're trying to fit maybe as a sequence of best linear approximations, local ones. And there is a range of work actually trying to find the best sample points for this, right? You want to find what kind of stability properties it has, try to see how changing the points changes your approximation, and kind of the stability properties that come with this. And I personally also think the reason a lot of these ML methods work so well is specifically because piecewise linear approximation functions have better stability properties. You can bend them in ways that you wouldn't be able to do with smooth functions. And if you think of each phase as a piecewise of the piecewise linear function as a best linear approximator, then this is again reminiscent of the gradient estimation problem, right? We're trying to ask, okay, which data points to choose to get the best phase, which we could interpret as which points to choose to get the best gradient. And by using our understanding of the sample set, we might actually be able to inform the sample set selection for these kind of problems as well. So I think I've come to the end. I want to thank you guys for listening to the talk. I hope I showed a bit about the gradient estimation problem and how it can be applied to different fields.
Yeah, thank you very much. Thanks, Daniel. Any questions? Yeah, no questions. I have like maybe like a small question to related to what you just mentioned about like justifying piecewise linear functions as activations functions.
Yeah.
Yeah. So can you push this a little bit further by trying to see what is the best activation function based on this kind of results? Because here you said that okay, we know that piecewise linear functions are efficient, and this can be justified by our theory. But assume that I give you like what would be like the best activation function according to your framework, if you see what I mean.
Yeah, I see what you're saying.
Yeah.
And I think it would be, I think the way to look at it from what we were saying is, I mean, it comes back to why we chose the simplex gradient as an approximator for your gradient. In essence, you could choose maybe a quadratic or a third order derivative and fit that function and take the gradient of that. But in the presence of noise and other instabilities, you want something that's very stable, that like approximates your prior well. And I think this is also something that motivates the activation functions. You want to stay sort of linear in that region, and you want wherever you bend your function essentially to not overbend or have an influence in other regions too much. You don't want this Runge phenomenon that you have with polynomials when you have points that are too closely put together. You want to have this Chebyshev spacing to make this to get rid of that. And I think this is really the insight I think that I gained from this there. I'm not sure how you would use the actual sample point selection for those. I think you could motivate it and by some linearization or something. But I think the real answer here is the choice of using linear functions locally and thinking really about what a function approximation should do locally. If you don't have any strong prior on the, I guess this is the other thing. If you don't have any strong prior in your function, locally, you always know that your function is going to look like a polynomial. So might as well use that insight.
Mm. Yeah. Okay. Yeah. So like in a way, you are suggesting like piecewise linear are really the best. Yeah.
Yeah, I mean, and it might make sense. I would like to study it from a stability perspective of like how much you bend it, how much that enforces
Yeah.
things. But yeah,
Yeah.
I think it make a lot of sense.
Okay. Okay. Makes sense. Yeah. Other questions, just in case? All right. Yeah, seems
All right.
done. Yeah, thank you, Daniel, very much for the nice talk, and thanks everyone for